All right, welcome everyone. I think we can get started. Today we welcome Marsha Chechik. The title of her talk is on Safety, Assurance, and Reliability, a Software Engineering Perspective. Marsha is a professor and chair in the Department of Computer Science at the University of Toronto, and she received her PhD from the University of Maryland in 1996. Her research interests are in the application of formal methods to improve the quality of software, and she has authored over 200 papers in formal methods, software specification and verification, computer safety and security, and requirements engineering. Marsha has been on many committees, including most recently the Program Committee co-chair of the 2021 International Conference on Foundations of Software Engineering and 2018 International Conference in Software Engineering. Well, without further ado, we welcome Marsha and we look forward to hearing your talk.
Thank you so much. Thank you so much for inviting me. As I'm going to talk to you, my goal here is to tell you about a number of different projects that we were doing in the space of safety and assurance and reliability. Some of this can be technical. There is no reason why it needs to be technical. Feel free to interrupt me whenever you want. Really, my goal here is much more to tell you what are the scope of problems we're looking at in this space, rather than necessarily communicate any of the technical details of any of the solutions. First of all, how did I get to these things? So I started my work in program analysis, basically, and I've been looking at that for a while, doing some formal reasoning, model checking, theorem proving, various other forms of software verification. I was doing some modeling, including modeling of product lines. I was interested for a while in all forms of reuse of analyses, reuse of results, etc., etc. And then this combination of interest about reasoning and about modeling and about reuse brought me about 10 years ago in the question of safety of software-based systems, and specifically automotive systems. Now, why automotive? Well, because they are complex. So there is a whole lot of software complexity. There are millions of lines of code in cars. These systems are ubiquitous, so most of us need to drive. There is a ton of even end user configurability. So companies need to maintain a complex product line, and building and testing an individual product is really infeasible. And of course, these cars are increasingly becoming self-driving, or at least including self-driving features, making reasoning about safety of them very timely and very important. So you probably all know about the recent autonomous driving race and its failures, including the Tesla Model S autopilot fatality in 2016 and in China and the US, and then another one in 2018 and another one in 2018 again in the US. These fatalities got a lot of people in the community thinking very hard, what can we do to ask the question of what is considered to be safe? And how do we make sure that that safety is in fact achieved? In general, the notion of safety is quite nebulous. And this is one of the questions we're going to be trying to answer as part of this talk. So in addition to self-driving, there are a lot of other interesting safety critical systems that include some form of machine learning parts, for example, such as delivery robots or luggage robots. And not all of them, of course, are as critical as cars. So I am a little concerned when the luggage robot hits me, but maybe not quite as much as when the car hits me. Now your individual mileage might vary here, but this broad range of systems which we're building and that are following us around do need a notion of means for them to be safe and secure and dependable, and this is what I'm trying to do. So first of all, let's talk a little bit about assurance. And in this, I'm going to start with the question of safety. So safety is defined as absence of unreasonable risk. And we calculate the risk basically as a product of severity and likelihood. So we want to know what is a crash, what is a hazard, and then what is the risk that we can estimate about these negative events. And everything in safety is about minimizing such risk. Okay. Now, given the broad interest of companies that develop high assurance systems that are required to be safe, there was a broad push in development of standards. And standards are documented agreements containing technical specifications or other precise criteria to be used consistently as rules, guidelines, or definitions of characteristics to ensure that materials, products, processes, and services are fit for their purpose. So here are some examples of these things. One is for medical device software that define the software lifecycle processes. Another one is for software considerations in airborne systems and equipment certifications, absolutely a de facto standard these days for all new aircrafts. And the one that I'm going to mention a little bit more is ISO 26262, which is the functional safety of road vehicles. So if we look at the way that these standards are defined, for example, ISO 26262, what it's doing is it's developing a process. And this process is forming a letter V, as you can all see. So starting from the left, we begin with some hazard analysis. So we define what could be some of the hazards. We then develop safety concepts. Then we build the architecture. Then we do the hardware software development. Now we're done with the product. That's one side of the V. And on the other side, we start validating all of this. So we're defining verification conditions or some testing, and then at the end, do the overall vehicle validation and testing. And underlying this whole process is something which is called a safety or an assurance case. And this is going to be a focus of a lot of what I'm going to talk about. So these safety or assurance cases, also security cases, privacy cases, whatever we decide is the topic at hand, is the reasoned, auditable artifact created for contention that its top-down claim or a set of claims is satisfied, including systematic argumentation and its underlying evidence and explicit assumptions that support this claim. That's kind of the definition of this assurance case. So what that means is we're building some sort of an argument starting from the goal we're trying to assure, and we keep on refining this until we can collect evidence that the goals have been met. Now, the evidence can come in many forms. In my world, it is a lot of test results or analyses, results of model checking, but it could also be expert opinion or some sort of a link to a standard. And the argument itself can also be quite informal. The argument basically can be deemed as sufficient or adequate. So these are not very formal statements. They're really quite informal. In General Motors, which is the company I work with, assurance cases are often developed in Word and take multiple thousands of pages of text. Now, I'm sorry to say I don't know how to reason about thousands of pages of text. So what we and others try to do is develop methodology that is a little bit more graphical, a little bit more analyzable, a little bit more reasonable in this space. So specifically, the de facto standard in this area, other than text, is something called goal structuring notation, or GSN, which is a notation for structuring this assurance case and linking argumentation, rationale, context, assumptions, and evidence. And there is even some graphical, shapes for these things, for goals and context and strategies. And I think in some of my examples, the shapes change, but I'm going to have a legend every time to tell you what is what. You don't need to remember that circle is evidence and diamond is strategy. And let me give you a quick example of an assurance case defined at a relatively high level of abstraction for a real system. So this system is the lane management system. I am assuming most of you either have cars or have driven cars, and at least modern cars these days have this notion of the lane management system. It is a critical, self-critical, safety critical driver assistance system. It is subject to the ISO 26262 standard, and it uses a variety of sensors for the goal of, well, doing the lane keeping, so that keeps the vehicle within the lane markings, the lane centering, which centers the vehicle in the middle of the lane, or that signals the lane departure. That's when the driver leaves the lane, and then the system decides that this is unintentional and the driver should be alerted. So if I want to build an assurance case for this, a fragment of this is going to look like this. So the system is safe. I'm going to assume for now that this is non-rainy driving conditions. No snow, no sleet, no Canadian winter, none of that. So perfect weather. We're in Arizona, which is where a lot of these things have first been tested because of the perfect weather. Now we're going to decompose over all the different safety goals. We will say that this LMS system will always notify the driver if it fails. It always allows the user to override and take control. And also, maybe the system is also detecting pedestrians, and I'm going to throw this in that this also works correctly. And then I'm going to keep on going. I'm going to identify some hazards. I'm going to decompose over the different types of procedures. So before shutting down, LMS is going to alert the driver, and it will be able to detect failure in any of its subsystems. Then we're decomposing over user alerts, et cetera, et cetera, et cetera. Okay, so what this picture shows is, first of all, on the in the leaves of this argument, so it's all tree-like. So in the leaves is evidence, and again, from my world, the evidence is either static analysis, something that can be determined about software without running it, or it could be results of some tests, or it could be some sort of deeper verification analysis, or things like expert opinion or some other references. Overall, this is again an argument that ends up collecting all of those artifacts. So the good news is these assurance cases are very useful to software engineers because they allow us to combine individual analysis pieces into something that actually connects to the real system that runs. On the other hand, these assurance cases are quite informal. So it's not very easy to check that they are complete, that they are consistent, that they make sense. It's hard to maintain these artifacts. It's very hard to look at things incrementally. And, of course, as computer scientists, we love doing things in pieces and then connect the pieces and then say we're done. And safety is very non-compositional, so it actually defies all of our methods to do the standard divide and conquer approaches. And of course, these days there are some sort of ML components that live in most of these safety critical systems. That not only do we not know how to assure safe, we're even having trouble specifying what that safety means. So in this space, what I try to look at over the past couple of years is things related to the argument itself. So how do you establish that the argument is rigorous? What kind of analysis can be done on the argument? How we can think in pieces compositionally or incrementally, as well as how to facilitate reuse of the argument, since software changes and safety changes and environment changes, and to what degree can we reuse what we already know about the safety of the system. Now, the great things are things I'm not going to talk to you about today, because this is also not only analysis of arguments, but also synthesizing some of the argument, as well as repairing the arguments if something goes wrong. Now, I came to this world from the world of evidence. Again, I'm not going to talk much about it here, which is why it's grayed out. But my ongoing interest is developing of methods for evidence generation and composition and reuse. And I've also recently been playing with trying to apply the same idea in the world of machine learning components. And depending on my time, I'll tell you a bit about support for reliability of machine learning components in terms of developing these assurance requirements and evidence and assurance case templates. Any questions before we look into a slightly more technical part? Okay, what's an argument? Now I'm going to leave lane management system alone for a bit, and I'm going to instead wheel in a cute robot. So I don't know about you, I spend a lot of time at home these days, so floor cleaning systems are a relevant example, much more relevant than lane management. I don't really go anywhere. So this one is designed to clean and vacuum a floor. The floor can be grimy and or contain objects. And the objective is to vacuum the floor if it contains objects and clean the floor if it is grimy. And such a system also can fail. So if you're trying to clean a tile while it contains an object, may damage the floor cleaning system and cause unsafe behavior. Okay, so if I'm trying to build an assurance case, I'll say, okay, so this floor cleaning system never becomes damaged. I have a strategy which allows me to argue over subsystems. I'm going to say that the cleaning subsystem works and the vacuuming subsystem works, and I'm done. Well, not quite. So first of all, why is it appropriate to even decompose over such systems? Maybe I'm also missing some cases. Maybe I'm missing some interactions between the subsystems. Maybe I have failed to include some of the subsystems in the decomposition. And maybe I have some other argument fallacies. By the way, this little triangle at the end means this is not developed yet. So obviously, if this is my method, I can assure anything safe, and that is just not going to be very productive. So instead, we declare that these assurance cases are way too informal, and maybe we can formalize this better. And if so, we can automate some reasoning as well as help find bugs in this reasoning. And so this is one line of work that we were doing, trying to formalize core assurance case concepts and then categorize decomposition strategies by their properties, identify and prove conditions under which the strategies are deductive, meaning provable formally, as well as then generate deductive strategies and use some tools, and in our case, based on theorem proving, to automate all of this reasoning and then put it all in a box that allows users to interact with this box and get some meaningful answers. So I think I'm not going to bore you with formal claims, but once we kind of do our work, the pieces of the assurance case end up looking a little bit more full. So this is the very same piece of the assurance case, but now we're trying to say that we are decomposing over different parts of the domain. So my domain might include clean or grimy tiles, but no others. And I can try to separate my reasoning into the different parts. Formally, this looks a little bit more scary, but I'm not gonna, worry much about this. And here's another template. This one is for property decomposition. So if I have a complicated property, can I break that property into simpler properties? What do I need to show that the composition of those properties actually gives me what I wanted at the first place? And where does this live in the assurance? And then this one, I think, is an example of an inductive property, the one where we do proof by induction, actually, as part of the assurance, and trying to make sure we don't end up leaving any of the cases unexplored. So once all of this happens, you can now throw in an analysis tool on all of this. And so in our case, we use Lean Theorem Prover to reason about the formal assurance case and then build an overall proof automation pipeline where we have the encoding of strategies and system models, and then we end up parsing input and then checking using the theory improver whether we've done all of our reasoning correctly, and at the end producing either debugging information or the tactic script, which is basically something that the theory improver can run to use as evidence to check that we've done the analysis correctly. And so this particular floor cleaning system will end up producing the following assurance case. So we started with our original parent claim. We then have a whole bunch of argument in blue about formalization itself. Have we done this right? Have we done the appropriate parts, et cetera, et cetera? And then we have at the end the formalized strategy with links to parts of the theory improver that somebody can examine and say, yes, this is the right assurance case. Okay, so this is fine. Now, whoever wants to use this, there is this scary, math in the middle. Well, so once you know what you are looking for, so once the argument ends up being mathematically formal, all sorts of good things can be done once you make a change. So if the system changes, how much of the assurance case can get reused? Which is ultimately what at least General Motors has been keenly interested in, of course, because they're changing their software all the time, right? The safety case is hundreds of thousands of lines of text. If you make a change, what is impacted? What do you need to re-verify or recertify before the system is safe to go on the road? So let me tell you a couple of the things we're doing in the space of reuse. So one is the question of how to reason compositionally. So piece by piece by piece, and then putting it all together and say, see, we're done. Also, how much changes in the system can preserve assurance arguments, and how to prove that a change to one component does not end up affecting others. And I'm going to do this very, very quickly. So first of all, arguing compositionally, I have one component, satisfies a property. Let me build some sort of assurance case. Here's another component, satisfies another property. I build an assurance case. Here's a third one. Now what I want to do is I want to put these three together. First component, second component, third component. Those two vertical bars mean parallel composition. I'm going to put all of them together. And now I'm going to say, see, I was able to prove that my system is safe with respect to some hazard by combining individual proofs. Unfortunately, this compositionality is notoriously difficult. So safety is just not compositional. So basically, imagine that I have a component that works just fine. If you put another component next to it, it may end up interacting with mine in some funny ways. And any of you who tried downloading apps on a cell phone, for example, may have found that some apps end up interacting with your memory management, some others end up interacting with your security settings, et cetera, et cetera. So these individual pieces end up interacting with each other in ways that we can't easily predict, producing unsafe interactions. So those are called emergent behaviors. So these are behaviors that aren't in any of the existing systems, but once you put them together, they all of a sudden exist, and they are nasty, and they cause safety problems, and we need to find them somehow. And so the number of these potentially hazardous interactions can easily grow very, very fast once we put multiple components together. And so that's why reasoning about safety compositionally in general is quite tricky. So what we've been trying to do is find context where you can reason about this more effectively, and the specific space where we're building compositional safety is in the world of publish subscribe systems, where we have highly decoupled components and they depend on each other based on topics through which they talk to each other, not variables or processes. So in my floor cleaning system, I could imagine that I have a component camera and a component cleaner and a component mover, and they all talk to each other through this publish subscribe middleware. And camera scans tiles for grime and objects, and cleaner cleans grimy tiles, and mover moves the system across the floor, and all of this, works very well. And we have the very same hazardous interaction. So here's my system, and here are my rubber boots. The mover begins moving to the non-empty tile before cleaner has finished. And then we have ourselves a damaged system. So what do we do in order to prove that this is not going to happen? So the method here is to try to characterize the behavior of publish subscribe via contracts. So we can assign mover the contract. When the value on is received from topic cleaner status, remain idle until value off is received from the same topic. So that means don't basically make sure that the components don't interact in a way that you don't desire. And once you have such contracts, we actually can compose the reasoning about the system, the argument about assurance from the parts about the mover, the cleaner, and the camera, put this all together, and then have a formal proof that justifies this. So now one of the questions is, how do we go from floor cleaning systems to much more realistic systems? How to write contracts that each component can write in some meaningful way, so that the overall system can be compositionally analyzed. So work in progress. Another piece of reuse is a project that we've been doing for actually somewhat longer. And this is related to change impact assessment. So if I have a system model and it is connected to a bunch of safety cases, and I'm now changing the system model, how much of the new safety case reuses the old safety case? Or if you want, how much does the old safety case still stays relevant for the changed system? Okay, so basically what we're doing is we're doing impact assessment of the change to the model with respect to the safety case. So I'm not going to bore you with the technical details, but what this ends up producing, and this is another automotive example. So this is activating an actuator when a vehicle speed is greater than 15 kilometers an hour. Don't worry what is here, worry at the colors. So the color green means this particular part of the assurance case is deemed reusable given a change. The red means this part of the assurance case is not reusable. This is no longer valid and you need to redo it. And the arrow here means this looks right, but give it another, another review if you want, because something may end up changing. We're just unable to prove that it is okay, and we're also unable to prove that it is not okay. So basically, look at this one more time. And so the idea of this change impact assessment is to very quickly realize what part of the assurance case can stay same and where we're going to need human judgment, as well as what parts of the evidence may end up needing to be reused and which ones not. And actually, if you look at this picture, you see a lot of red and not a whole lot of green. And specifically, one of the things that you see is all of the evidence has been colored red, which means we cannot reuse all the evidence as is. And this is typical. So once a change is made, a lot of the assurance case ends up being rendered unusable. And we need to do additional analysis to check whether a change in the system allow us to reuse appropriate evidence. And that is what this next project is aiming to do. So we're trying to prove that a change to one component does not end up affecting others and therefore safety. So the method for this is based on program analysis. And we've been building a system called Clever, which receives a client, which is a system, and a library, which is an underlying component used by the client, and is trying to answer a client-specific equivalence checking question. Meaning, if a library gets updated, will that affect behavior of the client? And if it does, we get a counterexample that shows the impact on the client. And if not, then we get a reason or a proof for why this is okay. And of course, that proof can then be inserted into the assurance case for somebody to review. Now, here's a little toy example. I have the library composite. So this is version 1 and version 2, and they're completely different libraries. And the difference is in one of them, it returns count +1, and in the other one, it returns 1. So these are not equivalent. However, the way that the client uses this library is by comparing its return against 0. And interestingly, both of those libraries, if you compare them against 0, is it equal to 0 or is it not equal to 0, return the same value. Which means, since the only thing I'm doing is checking whether those two things are affecting 0, this is my reason why those two libraries are the same. Okay, so that's my reason for client-specific equivalence. And what I can do with this is, if the client is not impacted, then everything related to the client can now be directly reused. So basically, imagine that here I had a complicated program, and these were some changes. This was the old part, and this is the new part. Now, this significant potentially change to the program does not affect the overall functional behavior. And that means my whole testing, my whole verification, my whole analysis can be used verbatim as evidence in all of my assurance. And if not, so meaning I do show that that change matters, then the proof will tell me how and where it matters, and I can still partially reuse the evidence, which is very much the point of all of this work. Okay, so this was all the stuff on the level of argument. So again, once you describe it, once you formalize it, you can do all sorts of things with it. Put them together, reuse, handle impact assessment, etc., etc. Now, what happens if all of these programs aren't just developed by developers, but perhaps are part of machine learning components that, of course, enter our safety critical systems? Is there anything that can be done there? So first of all, ML and assurance aren't really friends. And I know that there were some talks in this series about this topic. So basically, on one hand, ML is very appealing in its ability to learn and generalize beyond training data, but you never answer anything with 100% certainty. So we don't even really know whether something is a vehicle. What we learn isn't generally understandable by humans. And of course, we're trying to build these assurance cases, which are all based on human reviewability. They're prone to adversarial examples. And also in my field, there is very active work on trying to reason about safety, about correctness of machine learning components through testing and through verification. So there are many techniques that are developed to try to look at the structure of the programs that build machine learning systems and try to test them or try to verify them. They don't work very well because, of course, the neural nets that we end up producing are just bigger than any of the systems that we're able to build for their analysis. And we're also struggling with this topic of what does it mean to be correct? So what is it that we're assuring? And so with this, what we've been studying is the topic of reliability. And so I'm looking at the time, and I am like 43 minutes into my talk and about 20 pretty technical slides ahead of me. So I'm going to try to run through them with the goal of saying what we're doing rather than how we're doing it, so that I can leave some time to for us to discuss some questions. So the idea here is we're trying to develop the notion of specification for reliability. So basically, given a realistic range of environmental changes, what would it mean for the system to be reliable? What is even the definition of this? We also are interested in a method for generating reliability satisfaction evidence. And then finally, we want to put this evidence together to build reliability assurance cases. And so this is relatively new work that we're doing, and the focus here is on computer vision components. I think I'm going to skip the related work on reliability for now. I'm happy to return to this. And so the approach is that we're trying to see, as the systems get perturbed, how much perturbation is reasonable for the machine learning component to still act correctly. And we do this using human performance as a baseline. So the question we're asking is, if the changes do not affect humans, then they shouldn't affect the machine vision component either. So we're trying to identify a class of safety-related image transformations, simulating realistic changes, and then trying to specify some requirements classes for parameters that are based on human performance. So the transformations come from something which is called CV-HAZOP. This is a checklist with difficult and performance decreasing situations that are systematically defined in the computer vision domain. This is a whole checklist that includes a perception pipeline, so light sources, medium, object observer, and algorithm. And then there are various hazards that can happen and how information ends up being passed between the portions of the pipeline. And then for each location, we get this list of entries describing possible hazards. So for example, if I look here, the entry number 184 describes reducing the transparency of the medium, which means making the medium optically thicker and thus leading to a decrease in contrast. So we then say that an image transformation is safety related if it can produce a negative impact on this vision pipeline locations. So some of the examples of commonly used safety related transformations are frost, contrast adjustment, etc. So for example, the contrast adjustment might end up reducing lighting in the scene and thus can cause various errors and the subsequent system failures. So for example, suppose that I start with this car, okay? I'm now gonna add a transformation, and that transformation is gonna be frost. So if I add it for a little bit, that's a relatively small change, and we can all see that this is all fine. If I add some more, I can still see the car, but it's getting more difficult. But if my entire windshield is fully frosted, I don't see any car. So it is unreasonable for me to expect that any system will see the car under this level of transformation. So this is no longer reasonable. And so what we're trying to do here is define some way of looking at visual changes between images. And for this, we're using a concept which is developed in the computer vision domain, which is called IQA. And then trying to define how much of that change might end up being reasonable. And the reasonable part, as I told you, comes from human experiments. So we're trying to see what are the thresholds of these visual changes that shouldn't affect humans. And so what we've done is we took 2,000 humans and ran experiments on the Amazon Mechanical Turk, giving these humans forced choice image categorization tasks. The tasks are timed to ensure fairness in the comparison between humans and machines, and basically asking them, given the different transformations, to identify if something is a car or it isn't a car. And so we ran this through 8 safety-related transformations: the color, RGB, contrast, defocus, blur, brightness, frost. That's the one that I'm showing here. Color jitter, JPEG compression, and Gaussian noise. And based on that, again, we got these thresholds. So with them, what we do is we now define requirements. So requirements go as follows. Suppose that I have a range of changes in images, and that range does not affect human performance. Well, then it is reasonable that the correctness of the machine component shouldn't be affected either. And so semi-formally, I have some sort of transformation. I have this threshold. That's the one that I measured with humans. I have a performance metric that measures correctness of output compared to ground truth. And I need ground truth because here this is correctness preservation. And then the rule is that the component under validation is required to have consistent metric for images transformed with visual changes below this threshold. Now I need ground truth here, and we don't always have it. And M should be chosen according to the type of components that we're dealing with. So for example, for image classification, this might be prediction accuracy. Now we don't always have ground truth. So there is another version of requirements, which is prediction preservation. And the idea here is that, again, given the range of changes that don't affect human predictions, the predictions of the machine vision component should also remain unaffected. And it looks very similar to the previous set of requirements, except I now have a slightly different metric called similarity metric S that ends up comparing outputs on both original and transformed images. And here again, as I said, I don't need ground truth. Those types of requirements, one doesn't subsume the other. The correctness preservation checks for correctness of decisions. I do need ground truth. And if my system satisfies only correctness preservation, what it might do is it might correctly recognize, but different objects. So maybe first time it correctly recognized the car, second time it correctly recognized pedestrian. And that's not quite what I want, but that's what the requirement is specifying. The prediction preservation is checking for preservation of decisions after the transformation. It can be checked on unlabeled images, which is way easier to obtain. But if I'm only satisfying prediction preservation, my system might preserve incorrect decisions rather than correct ones, and then end up changing correct ones because I have no notion of ground truth, which is why we ultimately want both. If both are available, then both end up being reasonable reliability requirements. So in the case for our frost, after all of the work that we would end up doing, is we would say, okay, our threshold is 0.84 for correctness preservation and 0.89 for prediction preservation. And then these would end up being our requirements once we end up adding the artificial frost. Now, once we specify these things, we can assure them. So that means we know how to instantiate the requirements. We now are looking to generate reliability satisfaction evidence, and we're doing this via testing. So I don't think I'm gonna spend much time on this. What we're doing is we are generating a bunch of test cases, going through the transformation characteristics, and then trying to assess how the system reacts given the test cases that we generate, and based on that, determine whether or not the reliability requirements get satisfied. So I'm just going to run through this. It's in the paper in case you want to see this. And then the requirements are satisfied if the confidence of satisfaction is over 95%. Once this works, one can then build assurance cases. So I will, again, skip some of the how we get to the part that talks about reliability assurance. But basically, the piece on reliability will end up looking like this. So this is the prediction preservation pattern. If I have the prediction preservation requirement, and it's going to be satisfied under the operating environment specified in the operational design domain. So here I'm going to do an argument over different classes of image transformations, simulating hazardous conditions in the operating condition. And my justification for the choice is the SV-HAZOP, I'm sorry. Then I will see whether the MVC under validation is required to have the consistent metric for the images transformed with visual images below this threshold that I determine using human experiments. And then I'm able to generate the test cases, and the test results would show that the S value has not decreased after transformations with a 95% confidence. And then I'm also able to provide the test data. This is, again, under the assumption that this is a known vision task, and I was given the particular prediction similarity metric. And so the things in bright orange are the parts where we've contributed the actual technical solution. And then something similar exists for correctness preservation, except I'm now also, I also need to assume that I have the ground truth. So at the end of all of this, again, I'm able to produce a reviewable assurance case, and we're able to collect the evidence for why this works, as well as the argument as to what was the right requirement and what made me think that this all worked so well. Okay, so the questions to ponder here are, I've shown you what works on image classification models, and there is more to life than image classification. Certainly by the time that I get to a real driving scenario, we got to generalize this quite significantly. We also have been basing our results on human experiments. They're quite expensive, and there's no way we can repeat them for every transformation and every type of analysis. So we're interested in various forms of reuse of this. And we're also interested in, now that reliability requirements say fail, what might be the methods for improving reliability using these requirements. Okay, so by the way of summary, the combination of techniques that are being developed, some in machine learning space, some in software engineering space, combined with arguments as a way of organizing a variety of activities around this notion of assurance case, aim to systematically decompose arguments, again, until explicit evidence can be generated. And this is a way of generating artifacts that can help us reason about safety of software. And I mentioned a few projects in this space. In terms of the outlook of the future, assurance case creation is expensive. So one of the things that we've started thinking about, and again, I'm no expert here, is using NLP methods for building safety cases, as well as traceability between system models and assurance artifacts. And then broadly, we're interested in argument understandability, compositionality, debugging and repair, as well as anything related to evidence. Evidence generation, evidence composition, evidence reuse, and broadly generalizing ideas for ML safety to reliability of complete driving scenarios, as well as other forms of safety. And if we can put our heads together on all the things related to reviewability or understandability of the artifacts we get out of machine learning models, that would be extra super helpful. And I think that's everything. Big thanks to members of my group and a number of collaborators that all of this is being developed with. Okay, I think Ron has a question.
Thanks, Marsha. You want to take your slides down so we can see everybody?
Absolutely.
Yeah, hi. I enjoyed the presentation, Marsha. Quick question for you. I think in your work on reliability of machine learning components, you're focusing on essentially kinds of distribution shift, but I think the kinds of transformations you're exploring are ones that I guess are sort of the easy case. The field already is pretty good at training models to be accurate based on these sort of known transformations. But the devilish ones seem to be the unexpected, right? Like, how does you filmed in a few cities and it doesn't generalize to a different city, or adversarial examples. Like, how do you think about approaching those less well understood cases as examples for reliability?
Right. So I think that there are several questions here, and I might be able to answer at least some of them. So are the systems trained against all known safety critical transformations? Probably not. They're trained against some, and we have played with a few data sets to try to see whether they satisfy the reliability requirements, and not quite. So there's certainly work to be done there. But the question of completely unknown safety. So I'm sorry, there were 2 points here. One was adversarial examples. So adversarial examples in general are relatively small transformations that end up yielding completely unexpected consequences. So here we're going instead for realistic transformations rather than small transformations. So the goal isn't to do adversarial. The goal is to try to see, if frost works and rain works and frost and rain works and all of this under low lights work, can you say what is expected in terms of the behavior of the component, and can you now validate that this works? So we're not interested in small changes. We're interested again in these relatively well understood but safety critical realistic transformations and their compositions. In terms of fully unexpected transformations, well, that one is a good question. I think so moving from one city to another city, which is the example that you used, is not quite what we're looking at. We're looking at, regardless of where you are, what is happening to your windshield, or what is happening to your weather, or what is happening to your light, and what should you expect, under what conditions do you expect correctness of the behavior. So I'm hoping that at least that ends up being transformed from one scene to another, or from one city to another. But again, the goal isn't to train the system to act correctly. The goal is to see what is the expectation of correctness of the behavior, so that you can say, yes, this satisfies it, or yes, this violates it. So I don't know if this answered the question. So.
Great. Thanks, Ron. I don't know if you wanted to come back in on that.
Yeah, I mean, I guess I appreciate that. I guess I can imagine adversarial examples matter, in the sense that we've already seen cases where malicious people deliberately exploit flaws. So, being robust against natural distribution isn't enough if you have people who are maliciously trying to defeat systems, which is one risk. And I guess just to unpack the point about cities, it's that so many factors can vary, right? Like, there's been videos of Tesla autopilot utterly failing in Vietnam because the conditions are so different on the roads there than it was trained under that the system immediately gives up. You've got all these vehicles not in lanes and swarming around, right? So, the distribution, that's not a simple distribution shift like a blurring or rain, but it's still, you want to build systems that are robust against, you don't want to try to certify against every road in the world, right? You want to sort of make sure that if you get a new road that you hadn't trained on, that you can still have some confidence as to whether the system will work.
Right. So, sorry, when I say that we are beginning to collect requirements for reliability, let me begin by saying these are obviously partial requirements, and starting from the known. So what I can tell you, and in software engineering, there is a big, I guess, push for what is considered to be expected, or what is considered to be a standard. So what I want to know is how much to expect. So how much change is too much change before software is not expected to work correctly? And what is the range by which that expectation should be there? And so for people who are training, let's say, subject to these transformations, how much training needs to happen before this is considered to be good enough. So what is that specification? Notice that trying to guide against malicious changes, it's a somewhat different question. At the moment, I'm trying to specify what is the expectation and what is the range of change under which something is expected to function. Where you are right is once we start combining well-behaved transformations and not so well-behaved transformations, some of the math that we're trying to build may not work so well, but let's see how far this is going to go. So as far as I know, I'm basically not aware of any other method that produces requirements for reliability. So if this is like this, the system is expected to act correctly. And once we start going from building these things to building arguments that can stand in court, which is in many ways the question of the assurance discipline, figuring out what is expected is a very, very significant question. How much is, what should you expect? And at what point should you not expect it? So do we expect that the systems work even for the well understood transformations with a fully frosted windshield, or not? And at this point, it's actually too much of a transformation, and we shouldn't be expecting our systems to make miracles. So in many ways, that's kind of where we're pushing on this, trying to understand what can be understood and trying to specify it as expectations on the behavior of the systems, so that if there is a fail, did we put the system in the conditions where humans also would have failed? And what should be our expectations of the machines once they're put in these conditions? Because perhaps this relative correctness rather than absolute correctness is all that we could conceivably strive for. So it's kind of towards that approach.
Great. Thanks, Marsha. Thanks, Ron. Kelly, did you have a question?
Yes. Hi, Marsha. Thank you. Very, very interesting talk as always. I'm interested in asking about the collaboration with General Motors, and in what capacity some of these have been transferred to them. Like, are the assurances? Is that something that's actually being used in a commercial way, not necessarily General Motors, but to what extent it's being in that?
Okay, so that's a good question, and the answer is ish. So my the conversations I have about models and properties and structured assurance cases and all of that, well, there's none of that in GM. However, what is in GM is a pretty significant safety culture. What is in GM is the insistence on reviewability of the assurance cases before they can be given to the regulator, before the system is considered to be safe to go on the road. What is in General Motors is this management of a massive product line of similar but different vehicles, with this big question of what to test, what do you derive, what do you test, how do you build enough assurance, and the huge fear of recertification given a change. So this notion of what you can conceivably set up for reuse, and what can you conceivably do incrementally, and what could you conceivably do compositionally, is an absolutely real problem. What else is real there? All the issues of identifying features and looking at interactions and trying to see, how to save the system from all of these interactions. And unfortunately, GM, like most cars, made a change from a bunch of hardware components which only interacted in a very well understood ways, exactly, from having this massive bus, the CAN bus. So everything in theory talks to everything. And that makes any notion of compositional assurance, compositional reasoning, compositional arguments quite tricky. And you probably, have seen examples of stories where people were able to, I think, hack the engine by manipulating, the I don't remember, the app outside the car. Like, everything's connected to everything, and so this complete connectivity makes a lot of this assurance very, very cumbersome. Are they using our reliability requirements? No, of course they aren't. Are they building assurance cases? Yes, they are. Are they doing them in GSN? No, they don't. Are they interested in going from where they are to GSN? Yes, they are. So I don't know if that answered your question.
Yeah, very clearly. So I also had, just to follow up on that, because you talked about the legality of things, and again, I'm talking about collaboration, but when I was working at IBM doing collaborations with academic researchers, we never considered the legality of things, really. Well, I'm sure the lawyers did, but we didn't really. But then I did this project with Bombardier Aerospace, and they talked about how if they were to do a collaboration with an academic researcher and something catastrophic were to happen with an aircraft that had this collaboration as part of some of the software or even hardware in that regard, then that there'd be this notion of liability translated down to that research team. And I'm wondering if that's something that comes up in the GM conversations.
Well, so thank goodness they don't trust anything we build. So they trust our ideas, they trust our demonstrations, but if and when they choose to use any of the technologies, they want to build their own, or at least get a third party to build their own. So I guess in that respect, I'm less worried about being personally sued for any particular thing that GM does or doesn't do. But this notion of blame attribution is a big one. And in the case of OEMs, blame attribution to third-party supplier, the change in something. That's why, this question of clever, so this component upgrade came up, which is, if you have a third-party component or a third-party vendor that changes and it's now a new component, what is the dependence on whatever the OEM is building on this third party? So that's where that project came from. So a lot of that is absolutely within GM. So legality and blame attribution. Because I think given the number of cars on the road, each failure is really, really expensive. So I think that they're very keen on making sure that that they can limit the level of their exposure somehow.
Thanks, Kelly. Thanks, Marsha. So can I follow up just on the legal framework of this? And maybe I want to ask about the legal and regulatory framework that this work is in. So you mentioned certification. So I assume there's formal certification of the auto safety standards. But you also talked about, thinking about that legal liability. And so that's thinking, how would the legal system implement in this context the standard of, did you take reasonable care, or causation in the event of an accident? So I guess I want to think a little bit about your human subjects experiments and this reference point to, well, you can't expect the machine, the car to do better than a human. Have you got a basis for thinking that that's how the legal regime would think about this?
So
I guess I'm wondering why you're choosing that, or maybe I just want to sort of bring it out so we can talk about that. Is that the right reference?
Right. That's fair. So I am no legal scholar. And if I would say that, I firmly believe that this is the right legal argument, I should be called on a bluff. However, once people start writing down what are the rules of the road for autonomous vehicles, And at what point is the car, liable for an accident? You start asking what is expected. And once you have these cars on the road together with regular cars, it is expected that they do, no worse than the normal car given by the normal driver that abides by the rules. So I think in that respect, that particular requirement is arguable. So it's a reasonable requirement. However, once we have, mostly autonomous cars on the road, the answer might be that no, actually, we need the reaction from a hazard to a stop needs to be at least 3 times faster than a human. But I think the point is connecting requirements to a human baseline. In my case, direct. In some future, direct divided by some number is probably fair, because I frankly have now no other frame of reference.
Yeah, I guess I want to sort of think about this. So in the human subjects experiments you're doing, are you collaborating? You showed your team. Are you collaborating with social science on that in the design of those experiments and in the?
So this was, no, I'm not. This was a pretty quick and dirty mechanical Turk sort of forced choice experiment, which was really trivial to design. Once we start looking at something a little more interesting, I think a collaboration would be very, very useful. And the rationale was only, do we get meaningful answers from a trivial task that we give to humans? And yes, we do. How non-trivial should the task be? Do we care whether the people on Mechanical Turk are younger or older, or more able or less able? Are we defining what we expect out of autonomous vehicles based on reaction or ability of a bunch of 25-year-olds who happen to be the Mechanical Turkers? To what degree all of that is transformable against the population? That's a completely different question that we haven't started addressing. And a very valid one.
Right. So, because I think this is something we're starting to think a lot about at Schwartz is, how do we get the interdisciplinary teams that can really say, look, we're now moving into the domain of what would humans judge to be a good assurance case. For example, you mentioned at the outset that there's a lot of judgment in here. There's informal standards. At some level, there's a community of practice of deciding what is an adequate justification, what is not, what satisfies our assurance regime. And as we move into these domains, just thinking that, so we've been talking a fair bit internally about, how do you really integrate this kind of work with the social science of understanding the way humans answer questions, for example, or how they evaluate, trust in a domain like this. I actually think that there's a good likelihood that humans will expect more they will have a higher standard for autonomous vehicles than for humans, because they've all been that person with the frosted over windshield and taken a few risks. So they may cut each other slack in a way that they say, no, but you designed this ahead of time. You could decide, you made a choice, an engineering choice.
And I think this is actually exactly the right question. What is the society's expectation on reliability or of other performance of these autonomous vehicles relative to humans? Do we want them better, much better? Do we want them perfect? What do we as a society want? Again, I put a line in the sand and I said, well, kind of same as humans. We can argue, and maybe we should argue what we expect. But again, for the next few years, as we go through the hybrid world of some manned cars and some autonomous cars, what is this system gonna look like, and what are the rules? And do I need to know as a driver that the car next to me is driverless? Actually, for that, I have an example that you may all have heard that Waterloo had this autonomous car, autonomous, kind of going around the Belt Road, going and going and going and going and going and going, and collecting hundreds of miles and all of that. So I have a former student in Waterloo, and I was visiting him, and we were walking around, and then we saw on the road this big car with a leader, and he's like, "Okay, stop." I'm like, "Well, don't we need to? I mean, it's just a car. It will know, to stop in front of pedestrians." And he's like, "You know what? The word on the street is it might not. So we're gonna let this one pass, and only then we're gonna cross the street." So, in many ways, this training of cars in reality depends very much in the way that the rest of the world takes this training. And so, again, in the case of Waterloo, pedestrians knew to stay away from that car because they didn't quite know what to expect. So what I'm saying is, if there are more of such cars on the road, what are we doing? What are the requirements? What is safety? I actually don't quite know.
Yeah. It's reminding me of visiting at Harvard and being told, as if you walk around Harvard Square, do not expect any of the cars to stop even if you're in the crosswalk, right? It's every person for themselves. Happy to take questions from others if you want to raise your hand. But let me ask another question, Marsha. So again, thinking about these regulatory regimes. So the regime you're talking about, and Ron was kind of getting at this, and you're flagging it as challenging in the machine learning context. They rely on the capacity to kind of identify the claims you want to make and then test ahead of time. So it's in the world of I do contract theory. So in the world of contracting, we think about, can I anticipate every contingency that might impact my contract and incorporate that into my contract? And the answer that we know in human relations is that no, you can't anticipate everything. So that's also why we have these ex post approaches. So like on the one hand, we have highly structured formal systems of claims, certification. And on the other hand, we have this tort law system that basically has one rule: do what's reasonable, right? Take reasonable care. and only ex post will we argue about what was reasonable, although your lawyers internally will work hard to predict for you. Is this reasonable? Is this not? And so you presented work that's sort of, saying how do we adapt this ex ante approach in the context of machine learning? Are there people working on other approaches, or I guess I'm feeling skeptical that we can map all the things we need to test and the assurance cases we need to make. I mean, as you say, in the vehicle context, particularly in the hybrid stage, maybe we're fine because we've already got extremely well-developed safety cases. But is there other work being done on sort of like different approaches that don't involve that ability to ex ante set out what are all the things we'll care about?
Right. So good, very, very, very good question. So let me first, I guess, begin with what are all the things we care about. So car companies have their biggest, most prized possession is the large database of everything that has been observed to go wrong in the lifetime of, in this case, General Motors. Okay. So there is this very heavily guarded list of hazards. And this is everything that could go wrong. So all of the processes begin with hazard analysis, which very carefully traces your design against absence of those errors, of those hazards. And yes, if you haven't anticipated it, you cannot deal with it. But over 50 years, or whatever, 100 years, however long the cars, I guess 100 years, 100 more, 140. There have been a lot of hazards. So and this is how all of that starts, from this list of failures. Now, is it reasonable to throw all of this knowledge out and say, okay, we've changed technology. There is no more notion of requirement. There is no more notion of safety. There is no more notion of hazard. And if your car wasn't reasonable, oopsie daisy, let's just, I don't know, oops. That's worrisome. And the reason is all of these standards and all of these practices and all of those lists of hazards and hazard analyses came from a whole lot of failures. And those failures took a whole lot of human lives with them. And I'm sorry to say, if there's any way to reuse that knowledge without checking the reasonableness and the potential casualties that might come with absence of that reasonableness, I am all, for it.
Yeah, no, and that's a really great point. If we say, we know this is going to be a dynamic process with figuring out how to regulate with this new technology. And this is as a starting point with the data that we have. Also, another argument for perhaps not allowing that data to be held internally within individual companies.
I'm happy to still give you the data, but that might not be deemed reasonable. So I don't know how we're going to.
Yeah, no, I think that's right. But it's also why I think, part of solving all these problems is also solving, or shifting our historical approach to the idea that a company like GM has the right to preserve the trade secrecy of its hazard database, or an insurance company, for example. I know that insurance companies also collect this data.
What certainly worries me is if we do away from all of these standards that ultimately evolved as we were trying to understand what we have and what we need and what we're going to do with it, and a whole lot of legal battles, and we throw all of this out and we say our only one requirement is reasonableness. I don't know. I'm kind of worried.
I agree. I think that's a great point. Ron.
Yeah, thanks. Related point, I suppose, is how do you think about, another difficult area in machine learning, which is the calibration of probability or confidence with reality. I mean, I've got to assume that some of your proofs are going to talk about, some sense of what's the risk of something happening, maybe a system's ability to only act when it reaches a certain level of confidence. And yet that's an area that's notoriously challenging in machine learning research, is being able to actually in some way calibrate something that thinks an 80% probability occurs, or build a system where you can reasonably accurately determine those calibrated probabilities. Have you looked at that? Is that an area of interest or agenda to work in that space?
All right, let me try to make sure that I fully understand the question. So what I am not is a machine learning researcher. My notion of probabilistic things here is, that of a pretty novice outsider. But what is true is certainly within assurance case world, the notion of probabilistic reasoning and confidence-based reasoning and figuring out how much confidence is about the right confidence has been reasonably well studied. What that means for machine learning is, I think, what we're all trying to figure out. How much confidence is considered to be adequate for a particular domain and a particular regulation. And I have no particular insights on this other than, we know that the machine learning components will be probabilistic. We know that the assurance case will have confidence rather than, yes, no associated with them. We know how to reason with probabilities and confidences and whatnot in the structured argument. What we don't know is how much is enough. Okay, so we also do know, and this is in the kind of normal, in the world of the normal design rather than machine learning, part of the places where confidence comes in is quality of testing and kind of in general quality of your evidence. Have you tested enough? What did you observe, et cetera, et cetera. And so in this space, there is an explicit notion of combining evidence for the goal of improving confidence. So you may end up combining, one testing method with another, or you may end up combining testing with analysis. This is less of the requirement in the automotive world. I guess they don't think of themselves as safety critical enough, but it is absolutely a requirement in aerospace, where the notion of confidence, the expected confidence before this thing is certified to fly, is expected to be very, very high. And once you add probabilistic outcomes out of machine learning components and how all of that ends up combining and how much confidence a regulator would expect is, I think, what we're all collectively, in the business of trying to define. I don't know. I randomly put 95th% confidence, but I mean, that's out of a hat.
Yeah, and then you have the Boeing 737 Max, and you say, well, your tests are fine, but if they're not being implemented or certified by independent certifiers, it may not work. Avery, you have a question?
Yeah, I was just thinking about the 737 Max case also. And so I'm totally outside this conversation. I would call this a very pedestrian question, but that's probably a bad pun in this particular context. Professor of English here, but my father was a test pilot for the Navy and talked a lot about autonomous systems and airplanes and how that structure of risk is shared across sort of who makes the airplane, who flies the airplane, the corporation, right? And I'm trying to figure out, I mean, I'm coming to this without any preconceived notions. But going back to the question that Jillian asked about tort law, wouldn't this sort of just redistribute the risk across the user and the corporation with so many users, right? Imagine everyone's flying a 737 Max, right? Rather than a few people. Doesn't that just redistribute the risk in such an unpredictable way that how is this being discussed? I mean, in a way, this just kind of repeats that question, and I'm not asking in a very smart way, but this is something I just can't quite imagine. I'm sort of a paranoid. I would be the person avoiding that. What did you say? The moose car? Yeah. How is this talked about in the?
So I'm just going to put for, our discussion a little Boeing, 737 as, that wasn't part of this talk, but I happen to have the slide in terms of a couple of the observed software engineering problems that came through the evolution and interaction with other features. That's just, for us to ponder. So you asked the question about shared responsibility. I personally have absolutely nothing to add to that conversation. I think this is much more for the legal scholars. The world I am on is the world of, or at least I'm contributing to anyway, is the world of acceptable risks as done by evolved standards. And whether this notion of acceptable risk is based on how the risk is shared, I actually don't quite know. I don't write regulations. I'm looking for ways of combining a bunch of analysis and reasoning activities to provide input, I guess, to the regulatory compliance reviews. But it is a good question. So, and there are even some evolution issues and what went wrong and stuff like that, in case you ever want to talk about that. That's a different
right.
Topic.
Yeah, that's great, Marsha. But I think it just comes back to, I think we're facing a world having to transform our approaches in regulation to, currently we say we've got this very structured process, we put stuff out there, and then we have a kind of a tort system that, kind of cleans up, which has worked fine for the 20th century. But maybe we need to be thinking about, how we integrate that human oversight, which you also mentioned, human reviewability in new ways. Marsha, thank you so much for this talk. Really very interesting. As I say, we are thinking deeply about questions of trust and assurance, and the formal verification and safety cases. I think is a really important part of the background here, and I think you're totally right that we have to be evolving from those systems. So I really appreciate your talking to us. Thank you everybody for joining us.
Thank you so much for inviting me.
Yes, wonderful. And Sheila McElraith will be our speaker next week. She's still settling on a title, but I have heard hints it will be on interpretable classification. So please join us next week, 3 p.m. We look forward to seeing you all then. Thanks, everybody. Bye.